Okay, and so I've put into our shared drive, here's it, Lapply filtering. You can look at that. And so you can just run through a few steps. You can see what's happening. So first, load phrapl, and then we're going to load data. So besides that test data, there are two other data sets in phrapl you can use. They just have migration arrays right now, not migration array maps. And eventually we'll fill that out with ones that have 5 pops and things like that. So here we have one that has 4 pops with no more than 3 free parameters. Okay. And if we wanted to, so we can see, verify that by listing everything in the. Is this big enough? Can you see?
Can you make it a little bigger?
Is this big enough?
Yeah. Can you make it a little bigger?
Oh, sure. Okay.
And you said this was in our Google Drive file thing?
It's lapplyfiltering.r.
I see.
Yep. Okay.
And you're just using all the other test data?
So we have multiple data sets. So test data was one data set.
Oh, okay, yeah.
And doesn't actually have simulated trees. It just has just the migration array. So since the migration arrays take a long time to make, we pre-compute them for people.
Okay.
And so you can see how big it is. So this has 14,000 models in it. Okay. And so you might say, I don't want to have to deal with all those models. I only want models that have no migration in them. Right, so how do you deal with that? Well, we have functions in there that can give you information about how much migration there is in a model, or how many free parameters there are in a model, or whether a model coalesces at the root or not. Okay, and I mean these functions are very simple. So the function we're talking about right now, is it tells you the fraction of the migration possibilities that are present. Okay, and it's one line. The function is this is the function, right? All this is a return statement. Just return this. Right, it just counts up how many of these are 0, how many are not 0. Boom, it gives the ratio. Okay, so you can easily think about if there's some function of the model that you care about, you can write your own filtering function like this that gives you that information. Okay, and so what I can do is I could apply that function, fraction non-zero migration, to every individual in my migration array. It's every model in my migration array, right? Doing that in a for loop is something you could do, and it's probably fast enough. But if you want to, be macho for R or whatever, you can do it with a lapply supply type thing. So if we do this, so that just applied that function for all 14,000 models, right? And create a vector of what fraction of migration rates are present for each model. Okay, so it's just supply, the object you're looping over, the function you're applying. That's it. Okay, and for R, sometimes you can get huge speedups by doing that. Okay, and I'll show you what that, so you can see what that is. So here's all 14,000 models and their migration fraction. Okay.
But what does migration fraction mean exactly?
Right. So if we think about we're thinking about this sort of population history. I could have this migration, this migration, this migration, this migration, this migration, this migration, and then this migration, right? And so there's 2, 4, 6, 8 possible migration rates. How many of those are set to be non-zero? Right, so are we allowed to have migration or not for those? Okay, and so, yeah.
In this example, we only have 3 free parameters.
Right.
Right.
But I expect this all to be the same value, but 1. Right.
Right.
So,
that makes sense.
Yeah.
Okay.
So yeah, so it's not counting like the number of different migration independent rates we have, but just like out of these, how many are free to be non-zero? Yeah. But if you cared about that, you could see there's ways of filtering for models that have at least 2 migration parameters. Yeah. Yep. And so I have this list, and then what I can do is find, the one that has the most migration. And And so all you do for that is scroll up. Yeah. Have an regression array, and it tells me which one has the maximum, which max, across that vector, and that's that model that has the most migration. I can do the same thing for the model that has the least migration, right? Which you see, has no migration. It has just a polytomy, so everything collapses, and then have no migration between populations. Does that make sense? Okay. Now, if we want a subset and only get those that have, say, no migration, I can use the simple step. So I have my migration array, right? I have my set of measures for all the models, so that vector of, that migration fraction, and I say, give me those that have that equal to 0. Or I could go, give me those that have it less than 0.1 or greater than 0.5. Yeah?
So one question that I have, and I'd love to get people's opinion on this, there's two kinds of migration. There's the migration that you can imagine among your terminal taxa, so the extant populations. And then there's the historical gene flow that occurs among diverging lineages. Mm-hmm. And for me, biologically, I'm more interested in the gene flow among current entities or the terminal taxa. And so how could we filter these big migration arrays to basically differentiate historical migration from contemporary?
Yeah, so it's black versus blue.
Right.
Yeah.
But with the fractions, you could have 0.6 represent some ancestral and some.
Right, and you could have a function that says, throw out ones that have migration here and only look at ones that have migration here, or vice versa, if you wanted to.
Right, because those are in different matrices, so you could easily distinguish them.
Okay, so the way to write that function would be then to limit the migration to a certain matrix or at a certain collapse point.
Right. But biologically, do you care about those sort of models?
Yes.
But so yes, you care about everything. No. So one discussion we've had among the developer team is whether we should throw this out and say all we care about is contemporary migration. We don't allow migration in the past, which of course makes it simpler. Mm-hmm. But would that bother you?
For instance, my lab's doing a study looking at previous river systems and topology versus contemporary river systems and topology, and seeing which better explains population structuring and gene flow. So we'd appreciate it if you'd keep the ancient gene flow calculations in. More models.
Well, you could also just choose not to sample those models too, right?
Yeah, exactly.
Yeah. Right, and that's what this filtering does.
Yeah.
And it might turn out that it's harder to estimate. There's less signal, I think, in gene trees regarding historical gene flow.
Yeah.
Anyway.
Well, I mean, that's the argument that Peter Beerley makes for using an island model for migrate, and it's basically that it's really hard to infer historical gene flow. So some of the simulation testing that the IMA team has done has indicated that as you move back into that tree, it becomes more difficult to estimate those migration rates too. But it is particularly relevant for some questions, of course.
Yeah. One thing to note is that when we're subsetting the migration array, note single brackets. Normally, we're on like model 17, it's migration array bracket bracket. But for lists in general in R, if you want to get a subset of the list, it's a single bracket, which I found out this morning while Googling it. Why isn't this working? But that's what you do. Single bracket. And of course, R is good for parallel stuff now. So there's a parallel library in R that's now part of base R you can use. Okay? And all our computers now have multiple cores. Right? And of course, big clusters like the one we're using even yesterday that had 64 cores. Right? So what you can do is detect cores, and so it says my laptop has 8 cores on it. And so if you wanted to do the same thing in parallel, you could use this function. Right? So instead of supply, you can use MC-lapply, right? Which is multiple core lapply. Okay? And then just make it into a vector with, and this will return a list I make that listen to a vector using this function. Okay, but what this does when I enter this command is does the same applying this function to the set of models, but does it on 8 cores simultaneously, so separates them out. And this is a fast calculation, so who cares? But for other calculations to do in phrapl that might take a while, it shows how easy it is to do stuff in parallel. Do those embarrassingly parallel things. Yeah.
Did you specify how many cores, or is that just do all of them? Is that
I did. So
two?
MC cores equals the check cores.
Okay.
And so it checks and does that. I can also pre-declare. I could say MC cores equals 5 and leave 3 cores free.
Okay.
Yeah. You could do MC cores equals 200.
Okay.
And it wouldn't fail. It would just, each core would get multiple things trying to run on it.
Okay.
Yeah. Yeah.
And this could be spread out across cores on multiple different nodes or processors on a compute grid.
That makes it harder. So you can do that in R, but not with the MC apply.
Okay.
That's using like the snow types, like do snow, things like that, which is something I haven't played with much. For that, at that scale, what I typically do is have Nathan do it across batching software.
Yeah.
Right? So
Yeah.
if you're using SunGrid Engine or Condor or something like that. But if you have something that's like MPI connected, you can do that stuff within R.
Yeah.
So,
Cool.
yeah. Other questions about that? And just stupid here. So if I want to make sure that they're the same in the same order, right? Because you worry about if they're going in parallel, is it going to kind of switch the order of the vectors and stuff? And no, it does not. Right. So the same number for both. So that's good. Nothing I'd worry about. So any questions about that? So how to filter models, how to run things in parallel. Is that good? Okay. Now talk about performance. Oh, one cool note is now you can buy this. So last night I uploaded this. It's a single command to create a file you can upload to Shapeways. Now you can buy this model for $20. Or if you want
3D printed model.
yeah, 3D printed tree. You can get the plastic for $20. You can get it in solid gold for $14,000. There's a whole range of materials. So you can do your own. You just use write STL after you do your plot model, and you can have this file you can upload and print.
If we have leftover money in the NSF, we're going to get the solid gold one.
Yeah, earrings for everyone. But anyway, so yesterday we talked about how phrapl works. Now we're going to talk about whether it works, right? Which is something that, I mean, if you think about like nested clay analysis, like this is a great thing that no one actually tested until much later, right? So we're trying to test things as we go. So here's some simulations Nathan ran where we vary the number of loci we're using, so 10 versus 20 versus 50 versus 100, okay? As well as varying the true, time of splits and migration rates between models, right? This is a 3-population model, is that right?
Yeah, and also those NMs are actually 4 NMs. That's a mistake.
Okay. Okay. And so in each case, the red dot is the best model, right? And the true model is always 1. So we have some measure of similarity of models. Because I have 78 models, how do I put them on one axis? So put them on an axis based on how similar they are in parameter space, right? And so if the true models, so here it's great, right? So the true model is the best model, right? Here, not so good, right? The true model is over here, and we are somewhat similar to the true model, right? And as we increase the number of loci, we're often doing pretty well with 50 loci, right? But not always, okay? And here's 100 loci, and similar story. And how it gets it wrong is interesting, and I forget how it does, but Nathan knows. Like when it gets the wring model, how's the model?
I haven't actually organized that information. I mean, I think a common thing that it does get wrong is the best model will have historical gene flow, even though that wasn't in the simulated model. Again, possibly because it's hard to, it might just be a random thing where just like by chance a historical gene flow model, fits better or whatever reason, but it's not due to actual signal.
These axes, can you explain them a little more? So AIC weight is a similarity to the true model. So
AC weight is just like for all the models you can get their weight.
Sure.
And plot them that way. It's the highest one's red. Similarity to true model, is that based on just number of differences in the migration array? Yeah.
Yeah, it's basically
what are the points?
So these are all different models. So each point is a different model used for the same data set. So you simulate a data set, apply the full set of models to the data set, and then plot each model as a point.
So on the upper left-hand plot, the true model is shown in red. It has an AIC
No,
weight.
the true model is shown. The true model is always here.
Yeah, the red dot is the highest weight model,
Okay.
whatever the truth of that is.
Yeah.
So there's some model that's not the generating model that has an AIC weight of 0.8.
Right. I mean, right. So in theory, you want to have the true model recovered all the time. I mean, you could argue in some cases if you don't have enough data, you don't want to fit a model that's too complex. And so, if I have 5 data points and the true model has 20 parameters, I shouldn't be trying to fit a 20 parameter model. But at this scale, we have 100 loci. We should be out of that zone, right? So we should be getting the true model back. Right. And
So the x-axis is similarity to the true model.
right.
How are we measuring similarity?
So it's go ahead.
Yeah, and it's based on, in this instance, I mean, there's basically, if in any way that a given model differs in kind from the true model, it gets a penalty. It's sort of a dissimilarity increases. So if the number of migration rates differs from the true model, then that's 1 penalty point. If the populations in which migration is assigned differs, then that's another dissimilarity point. If the number of collapses is different, that's another. If the populations that are collapsing, even though the number of collapses is the same, that's another penalty. So it's stuff like that.
So it's basically, if you're thinking about doing the model averaging, right? Well, so they have certain parameters in common. You can average them, but some parameters aren't in common, right? And so that counts as a.
And so each of these is a single replicate.
Yeah.
Yeah, and I mean, I have 10 of these running, or they're probably done by now, that we might get a better estimate of performance instead of just by looking at one replicate.
And these are with the, the perfect known gene trees as well. And so one thing we're going to be doing after this is taking realistic rates of substitution, slapping them onto the gene trees, simulating data, re-inferring the gene trees. And so you have that aspect of the uncertainty too. Because in real life, you don't have the perfect gene trees. So this is an overestimate of how well it performs.
One last question. How many models are in the comparison here?
78.
So the 78.
It's the same 78 that we use for the empirical data sets.
Yeah.
So just to figure out how to read this, if you're looking at the bottom right-hand corner, the AIC weight is very similar between the true model and the highest weight. Would you still choose the orange dot over the true model?
That's still a better model based on AIC. Now, if you're writing an empirical paper, you shouldn't be, this model is the model and ignoring everything else. You should say, okay, there's lots of support for this model and this model. They differ in this parameter. Why might that be important?
Okay.
Yeah. Yeah.
So you mentioned that it might be in some of these cases that the presence of, or the inference of historical migration might be leading to the discrepancy there. So if you were to rerun these with only the subset of models that don't include that, would you expect to see with increasing numbers of loci greater agreement then between the highest ranked model and the true model?
I think so. I think some of the high weight, the weight for the true model would get higher, I think.
So potentially in empirical systems, if you have some justifiable reason why you don't expect to have any historical migration, I guess more loci might be better.
Yeah, I mean, there's things that you can filter out. If models just don't make sense given your particular system, like if you feel like you have a good sense that, you know, you have a fully resolved tree and you feel like you know what that topology is, I mean, I could see you, you know, focusing on a specific topology, and you're probably going to get a better estimate. I'm assuming you're right, but you're going to probably maybe get a better estimate of the true model.
Can you flip through these again now that?
Yeah.
Because the more, I think the more models, the bigger the model set you have, the harder it's going to be, the less likely that, like, assuming there's actually a true model under which, well, I mean, there probably was, under which a data set was generated, you're less and less likely to have that be the one that has the highest weight, just due to chance, I think. So the more you can narrow down the model space to weed out sort of, you know, bad models or models that are pretty similar in a way that you don't really care about the fine detail between models. So you're sort of only including more distinct models, the more likely phrapl is going to perform well, I think. Not everyone would agree.
Yeah, I mean, so like a lot of these models, like, so you have like, so we could flip, you know, let's assume this migration rate is 0, or very close to 0 in reality, right? So you can try models that have this being 0, both being 0, and, you know, in practice on your, you know, gene trees, you might have had only a few things that cross that via migration, right? And so, yeah, you shouldn't be able to distinguish those models well. And so what you should do is have all those models have about equal AIC weight, right? And which is then low. But again, with multi-model inference, you're saying, okay, well, they're all like this, but look at the actual parameter values, they're all small. So yeah, I mean, for each model, the estimate of the precision of how you estimate the AIC should be the same. Maybe you can afford to simulate more trees if you have fewer models or something.
Yeah, definitely. That's one advantage.
And
Yeah.
what was the true model here?
Yeah, can you draw the true model?
Yeah.
And also, so with this simulated data, this is all the gene trees are known without error, right?
Yeah. So we're going to, before we publish a paper, we're going to do it again with the actual simulated data for the gene trees. And see.
Well, the tricky thing here is that with potentially 78 true models, it's entirely reasonable to expect that some models are more complex to infer than others. Mm-hmm. How do we, you know, do we do all 78 1,000 times each with the different numbers of loci with estimated empirical gene trees? I mean, you know, it's challenging from our perspective to try to figure out the best way to test this even, right?
Yeah. But as users, I mean, so I mean, you should be critical, right? When you say, okay, how should I spend my research effort on getting data and running analyses? So what would make you convinced that this is a good enough approach to be worth your time? Besides your personal affection for us.
Or do you look at this and think, no way, I'm even going to bother? So that's the kind of feedback that would really appreciate from you guys is, you know, how can we test this in a way that makes it meaningful to you?
And this might be a dumb question because you mentioned the true model. So since this is just a simulation, you arbitrarily picked the true model? Okay.
I think this is a consistent true model across. Yeah, I mean, that's what Nathan's drawing.
Okay.
So you could do it such that every simulation you choose a different true model and see how often the simulations recover the true model. That's a different way of doing it. And in our initial work up to the grant, we did some that way and some a different way. Which would you find more convincing as a user?
Well, I'm just thinking, like, if you're using your own data, you don't know a true model, unless you know a true model. But if you're just going into it blind, there wouldn't be any true model at all, right? So you wouldn't be going for that number one. You'd just be going for the highest AIC, and you would then assume that is the best model, then, right?
Right. I mean, so the reason to do simulations is, okay, I know everything, and so let's see if we get it right.
Okay.
Whereas with a lot of methods people develop, and they say, okay, here's an empirical study, get reasonable results out, yeah, it works. Mm-hmm. But that's not a strong test because, yeah. So,
Yeah, so the top row is our isolation only models. I mean, it's pretty simple. So you have two species or populations collapsing in tau, and it varies actually between 0.5 and 2 for this value. And then C, the third population collapses later on, somewhere between 2.5 and 6. And then the next two rows is the same model. The only difference is you add migration rates, which can either be 4.5, 0.25, or 4.5, between the two closest related populations.
And again, we sort of pick the parameter values to be ones that Brian said were reasonable. But it's still challenging, right? I mean, so you could do it such that you have like huge taus and huge migration rates or no migration rates. Like, hey, we win, but we don't want to do that. But other parameter values that you folks think would be more reasonable than these?
I mean, just figuring out how to judge accuracy for this kind of thing is a little tricky too.
Right. So one thing you could do is the model average parameter values, and how similar are they to the true values? Which is different than saying, do I get the right model out?
Or the model weight of the true model.
Right.
To me, is a reasonable way to measure accuracy.
But to me, it's not, because I mean, you know, another model has some weight, so they're not trying to maximize it; they're trying to estimate it properly.
Yeah.
So, yeah.
I think if I saw this in the paper, I'd want to know like how often like the simplest model, so pure isolation, could be recovered, and then also like this model behind you where you have full migration at all time points, and how often you could also recover that, because that would be, you know, the most parameters and so the hardest to recover, right? So if you just had.
Yes, it has. So, because right now we have the top row has no migration, but you want to have another one that has all migration.
Right. Because you could potentially have that in an empirical system.
Yeah.
So.
I mean, it might be the case that we should be even more simple than this, and you know, can we separate an island model from a collapse-only model?
Yeah.
You know, predictably. You know, those are sort of two ends of a continuum that you could imagine.
But since a lot of users are going to be working in the area between the ends, you
Yeah,
know,
no,
you know, it works there too. Yeah. Okay. And one other thing people care about is, you know, will I graduate before this is done, right? And so here's using the same simulated data, and for each of the models, like number of free parameters and number of loci and runtimes. And these are runtimes as they are like as a single core job. So for each model running on a single core on a 3-year-old Mac Pro, how long did it take? Right? And you know, up to 10 hours, and these are like, you know, median and then 95% CI is the blue. And so, you know, if you have 10 loci, it's not that bad. Yeah, and 100 isn't that bad. I mean, it's almost like a linear increase, or probably better than linear increase. So
does this take too long? Would you run it for longer than this? I mean, I'm shocked at how fast it is. Makes me think we should run it longer and get better results.
Wait, this is for each model?
For each one.
this is for each model. Yeah, so you have the elapsed time for each replicate.
So if you have 10 hours and you're doing 100 models, then that's 1,000 hours.
Right.
It's like, yeah, on the right is 100.
This isn't for the full set of 78 models. This is
Yeah,
for each one.
okay.
Yeah.
It would
so-
take a while.
Yeah.
What about the number of individuals per loci?
Oh, it's good. The subsampling is 4 or 3.
It's always 4 for these. So there's 12 tip trees.
Yeah, that's a good point. Yeah. So I forget how much computer time it took overall. We can calculate that. We can just sum it up. But
On all of these?
yeah, of course. I mean, it's not. You're not going to. I mean, your situation as empiricists is you're going to have your 78 models or your 14,000 models and run it once. You're not going to loop over all possible combinations of parameters. So yeah.
And this is simulating 1,000 trees each time?
Is it
And
10,000?
1,000.
Which I feel is kind of low, but it seems to be working
I
well.
think it's
So
low for subsampling of 4.
It's low, but I mean, I've done simulations where I up that to 100,000 to 500,000, and it doesn't give any better, doesn't give any different results.
and that's the sort of data that you need as an empiricist too, because whatever the default is, you will not change, right? Maybe getting weird results you would, but yeah. And one thing you do is sort of like Mr. Bayes does with independent runs. You could try running 10,000 again and see if you get the same set of models out. And if not, then increase the number of trees again and do that again. Would that sort of thing be useful, or would a doubling of runtime at best? But
I think consistency is an important thing to me.
Yeah.
And so if I was running 2 separate runs and getting different results, that would cause me to question things.
Yeah.
Use the same random seed. That always works. Okay.
And runtime wise, for me, it seems it takes so long to get the samples and get the sequence data, and we all want to push it out really fast. But I mean, given what I think it has the potential to discriminate in our data, like I'll wait that long.
Yeah, sure. I mean, it's funny because
put it across a ton of cores.
Yeah. Yeah, so like, empiricists, you spend 4 years getting your data, then it takes a week to run. You're like, oh, it's so slow. Okay, cool. Yeah.
So one thing that I would see, or what I would like to run phrapl with, is as opposed to, like, let's say you were looking, and this is stuff I would be doing later on, and maybe this isn't the best way to go about it, but let's say you were doing like a rapid radiation or a large radiation that was rather recent, like geckos or anoles even. Anoles in like the Caribbean. There's a ton of them, and they're different species. And you have your tree, and they're all probably part of the same genus. And let's say you're even just doing like one little, like between a few forests on an island. Even then, you'd probably get like 9 or 10 different species, and you want to figure out like how they move around or what exactly is the biogeographical history of them.
So you want like an MS Bayes equivalent.
Would that be the best way to do it as opposed to use phrapl?
Well, I mean, someone else, you could use phrapl in that way where you have a shared population structure across everything and calculate likelihood for each species independently. And then, so does that make sense?
Okay.
So you could have say these models you care about for biogeography, right? And what you could do is apply them for species A, B, C, D, right? And so then you get, likelihood here, likelihood here, likelihood here, and here. And so you just sum them up and, plus, 4 times K, and then put it all into AIC. And so you can do that for each of them. And that gives you the total support for each of these models across all the species.
Okay. When that would be, because my concern was if you had like 10 species, it would take an infinite amount of time, but it would be just as well or just as
It would just work linear.
accurate to do it one at a time.
And then add the likelihoods.
And then add the
up
likelihoods.
the likelihoods.
And it's the same sort of math and would, okay.
Yeah, and it's just increased linearly with number of species.
Okay.
Yeah. I mean, the only issue with doing it this way, the way I've laid out, is that I could have different parameter estimates for like, tau for species A versus species B. So if you didn't want that, you could loop it a different way, and it'd be still the same complexity and runtime, but you can force them to have the same parameter values.
Okay.
Which one would you like more?
Well, I guess if you could force the tau itself, if you were to say knowing when diversification parameters were going down, that's, I guess, what I would use it for more so.
Okay.
Yeah.
And others who are thinking about this sort of question?
I think using the boundaries of the grid search as a way to enforce similarity in tau across all the species or something.
Oh, sure. The grid search automatically does this. So what you could do, right? So what we get here actually is, you know, the grid of likelihoods. The grid of likelihoods. And so one approach is to take the max here and the max here, which are different parameter values. Or you could say, I must take the max summed up across everything. So max here, 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 same position.
Yeah.
And so you do both that way, and it's the same, yeah. That would be perfect, yeah. So then you could leave it to the users to decide. It's interesting because I didn't think of that as a popular use case, but it seems to be.
If you were to take all those grids then and find the model between species, or between species, then could you take that subset of models and use it for the among species? So let's say you had like 10 species, but with that grid search, you found the proper model for all of them, and you were delineating between maybe like 3 or 4 models in between, or maybe even just the best one. Would that be a good way to do it? Because then you only have like a subset of 10 models per taxa.
It wouldn't save. Yeah, so what you could do is find the 5 best for species A and the 5 best for species B. You could do that and then take the combination of those. You could do that, but it's possible the best model is some sort of hybrid model that's in between.
Okay.
So if you have the compute power, I would just do all of them. But if not, it was just sort of a way of quickly getting at the best models.
Okay. Because then you'd still be activating like a population of 10, right?
And actually, it would still cost the same. Because for species A, the way you know that these 2 models are the good ones by trying all the models. For species B, the way you find out these 2 models are the good ones by trying all the models. And so you've still tried all the models, so it actually doesn't help you any.
Okay.
Yeah. Yeah.
I was wondering, instead of species A, B, and C, you do like replicates of the same species. If you can do the calculation of the overall likelihood as you showed there.
You could, but replicates how? How are you splitting the species?
I don't know. For instance, you run phrapl once and it gets you like the best model, and then you run it again and it gets you a different model just because there's like
stochasticity
in the simulated data.
That can happen, but that indicates a problem. That means you should be running out longer or something.
Okay.
It's like people who use Bayes traits, like for the trait evolution. The recommendation is to run it multiple times because it just like does a very bad job with like random starts. So you run it until you find it has the best likelihood, and then you're done. And that's a problem. That shows that the optimization is failing.
Okay.
And so so if that happens, you should do something
Could
more trees simulated or something like that.
Couldn't it be that you just don't have enough signal in your data? Like for instance, as she said, you have like true polytomies and.
I mean, not having enough signal is a problem, but the way that problem shows up isn't getting different best ones each time. You should have equally bad likelihoods, and so. And we'll go show you in a few minutes some empirical results from Brian, where he has very bad data, and you can't tell models.
No, I think there's 2 ways to interpret that.
Yeah, other thoughts about this, or sort of diagnostics you'd want? This is interesting. It's surprising that so many people asked for this. So, I suppose it would, then it sort of overlaps the space of MS Bayes, but.
I mean, there's really few good ways to do comparative phylogeography.
Yeah. Okay. Yeah.
Wondering quickly about in cases where you may have evidence for there being hierarchical structure in your data, if it would be reasonable at all, and to say, okay, I think I've got this initial bifurcation. Like, let me find support for that, and then if yes, then proceed to divide and
look at each one
look
separately.
within each one, and maybe it's not a bifurcation. Like maybe you test a 4-lineage model or something. Does that make sense? I'm not sure it makes sense to me, but I wanted to.
It's not crazy. I mean, it's sort of a greedy search in that you might miss the best model overall isn't found with that greedy optimization approach.
Yeah, but versus like going in and trying to use some independent source of evidence to split into subgroups that would then be tractable to implement in phrapl.
Yeah, because being better than a lot of other heuristics. Yeah. And you could automate that.
But I guess the sampling scheme for your initial or like most basal bifurcation would dictate how much support then you could find for further levels. So.
Yeah, but I mean, you could do something where so we have almost like BPP, you have a sort of maximum population divisions, and then we first start off by lumping them all,
right?
See what we find, and then find the chunks, and then go up that way. Yeah, because BPP works in that sort of greedy way.
Right.
Yeah.
Okay.
Interesting.
And we want to add the ability to sort of fix parameter values. So like you could fix like tau to be 0 and then compare that to a model where you allow tau to vary. And presumably if you have a much higher likelihood for a non-zero tau, then that suggests that these two populations are supported.
It's a species delimitation
that type of
approach.
Question.
Right.
Sort of similar to what you're asking.
All right, so we've also been running on empirical data sets too. So we have identified a set of 19 empirical data sets based on searching for like migrate or BPP or other things in the literature. And then a subset of those where people give us the data and analyze those. And so one thing we've done is look to see are the overall model, so you have our model weights on different kinds of models. And some models are isolation only, some models are migration only, island models, and some models have a mixture of the two. And one thing we've looked at is plotting those to see where life is, right? So if everything is isolation only, then isolation only models are fine, right? And of course, at deep divergences, human, whale, redwood, it's an isolation model, right? So by focusing on those data sets that have used BPP or migrate or something, we're looking at ones that are sort of in this area.
Our criterion for these empirical data were basically multi-locus, use some combination of IMA, migrate-in, and species tree approach. But, we didn't require that they used all three of them, but just at least one of them. And what was the other one? 3 populations.
Yeah.
So they're all 3 populations.
Yeah. And so we found that most of them are in this mixture of approaches. So it's not, it's not this, it might be this or this, but it's not that either. Okay.
So the plot here, there's basically, these are the model weights of isolation models cumulatively and island migration models cumulatively, and any model that has isolation and migration in some combination.
And there's actually 2 ways to do this kind of plot. One is a raw plot where you say, okay, what fraction are here for weight, what fraction are here for weight, what fraction are in the middle for weight. The problem with that is most models are here, right?
Of the 78, there's only 5 or 6 that are flaps only.
And so what this plot's doing is it's normalized. You have sort of the initial prior weight almost, which is then set so that it's here. And then we look at the normalized weights for everything else, which gets us over here to this. So it's an extra step. So it shows like how much we've learned about it. But so it seems like quasi-Bayesian. But the other way, I mean, if you have no data, run a model with no data, well then, since these models are most common, right, it's going to pick lots of those models. They're not learning anything from that. So that's why we did that. But
the normalization.
Yeah.
So looking at this, is it surprising? I mean, that so this is basically saying most empirical data, models that fit these data well have both isolation components and gene flow components to them. These are phylogeographic data sets.
It is or not? Yeah. Yeah, I mean, so part of it is you want to say, like, you know, why should you use phrapl? And part of it is like, oh yeah, it's a mixture of things that makes sense. Part of it is also like, wow, we discovered something new about the world. And the fact that things interbreed and collapse probably isn't a new discovery. But
Well, what's interesting to me is that almost all of the empirical data sets we looked at use species trees in some way as part of the analysis. And you know, certainly it's appealing, and that's why people use them. And yet there's very little argument, if you look at this, in favor of a species tree-only approach for phylogeographic data analysis.
yeah, it's true.
I think it was really striking with the other way we plotted the data.
Well, yeah. So here's the same results, but plotted a little differently. So for each data set, we have all 78 models, and they're ranged based on, you know, these are the pure tree models, right? There's 3 populations, so there's 3 ways of resolving that, plus a polytomy. So that's these models, and then there's various island models that have different migration rates. And then the rest of the models are ranged such that ones over here are more island-like, and ones over here are more tree-like. Okay? And then the area of the circles, not the diameter, is proportional to weight for that model. Right? So, you know, this model has 91% of the weight. So there's another little model here. And if one model had at least half the weight, we make it red, otherwise we make it black. And so you can see some data sets, you know, have, you know, don't distinguish models, perhaps because they have, you know, they're evolving under a different model, right?
So yeah, so Brian, you know, immediately assumed that our data were correct. And what I think is really going on, or at least partially going on, so there's probably real differences in the amount of information that different data sets have. It's really hard to evaluate this, and I think using different criteria, one might get different answers in terms of information. The data set, the Karsten's data set here, is from a plant species. It's 5 genes that have been sequenced in something like 120 individuals. So we have a big data set in terms of the number of individuals, maybe not so big in terms of number of loci. But all of our ABC analysis suggests that we need to parameterize exponential population growth in the species, which is, of course, something that we're not considering in phrapl. And so I think it's reassuring, actually, that our model support is so evenly distributed across all of these models, which are probably bad models for the system. And that's how I would interpret the fact that we don't have signal. You know, just that the models are not particularly appropriate for the particular system that we collected the data from. You know, it could be that something about the data doesn't have good information as well.
And granted, it's not going to be trivial, but do you plan to work in analyses of models that then incorporate
expansion
models of expansion and population growth to the paper?
Yeah, and probably not for this paper, but later. Yeah.
That just, I mean, that makes a whole other axis of.
Oh, totally.
Yeah.
You know, we're obviously struggling with how to present results and, you know, test that the thing works in the first place.
10 things at a time.
Yeah.
Well, do you have a question?
Yes, so I was curious about the results of that data set. So the AIC value is similar across all the models? That's
A bunch of little dots means that there's a lot of similarity, and so the overall model probabilities are not high for any one model. Like the House and Simmons data at the top, one model had like a model weight of 0.9 something, and that's why it has that big red circle. So that's a case where, for whatever reason, that model is really strongly supported given the data that they have. And in some ways, that's the best case scenario for a phrapl analysis, is that you find one model that has most of the model support.
In the previous slide with the triangle graph, so most of the models, most of the data sets in the literature kind of fall within the isolation with migration thing.
Yep.
But when Nathan did his simulations, it seemed that as you added the past migration to the models, the choice of model becomes kind of weird, right? I mean, the chances that you choose the true model kind of falls.
As you increase migration rate?
Yes.
Maybe. And this is 4NM. I mean, it's possible as you get super high migration rates, you're going to favor non-collapse over collapse models to some extent. Might be going on. I mean, once migration is so high, a model where you just have migration and no collapse might explain the data just as well, or if not better.
I mean, it seems that with high value of tau and high migration rates, you lose your power somehow to detect the best model. And I wondered if that has anything to do with the real data sets being showing that pattern of fitting the isolation with migration.
That would be good to look at. Yeah, look at how we're changed on that axis. The sort of triangle plots for these, and how does it change? Because I could imagine, yeah, if we have an old divergence and high migration and a lot of time for that migration, then most of the pattern comes from that migration. Because if we had a shallow divergence and migration only after that point, then yeah, that migration has been a lot of time for it. And so yeah, you can imagine at the extreme, all you see is migration, so you go to an island model only.
Yeah.
Because tau is really old, and so yeah. Maybe that's good to check. Yeah.
So on this figure right here, when you have like poor fit for any of these models, could it also be that perhaps you're not really defining your populations in a meaningful way?
Yeah.
So, I mean, all these presentations people give them, there's like, define my population is just based on what I think a clade is in a mitochondrial tree, or putting my populations in Hardy-Weinberg or subspecies or something, but that might not be meaningful, right?
Yeah.
So.
Yeah, and we trusted the author's description
Right.
of what these entities were.
Right.
Yeah.
You know, some of them did species limitation analyses, and some of them just didn't.
I mean, one thing we could add to the simulation is like, you misassign 5% of the samples, what happens?
Right.
I mean, so the question is that potentially of enough concern and that it could happen and could have a big enough effect that it's worth the simulation time to do it?
And I think the important thing for users to remember is when you say the model, it's not just the pattern of branching or collapse or gene flow or whatever, but it's also the parameter estimates that you use for the grid search. And it's also the assignments that you make. It's also, it's all conditional given the data that you put into it. So there are multiple ways to be wrong with any of this, of course. And, if you get a result that's weird, there's different things to look into.
And is there like a trend with a higher number of loci in the top and?
Good question. Mm-hmm. So here we see number of samples, base pairs per locus, number of loci, and SNPs per locus. And I didn't do a full correlation and stuff, but squinting at it, I don't see much. And maybe some interaction thing where it's number of loci times SNPs per locus or something, but we could do some sort of regression on this.
I mean, one of my secondary goals for this project is to find some way to quantify units of information for phylogeography. What is that? Is it the number of samples times the number of loci or times the number of SNPs? Or, can we make a statement about, because if we can do that, then what we can do is we can begin to connect the parameterization complexity of models to how much information you're putting into it. If you have the single locus data set, maybe you don't want to try to evaluate models that have up to 5 parameters because it's just hopeless. It's too much for the data that you're putting into it. But again, this is something that, to my knowledge, people haven't really come up with a good way to do.
You could do a reverse approach for that. So AICC, you put in your data set size, and what is that N? Is it number of loci? Is it number of sites? And so what you could do is find which N you put in best makes AICC an estimator of the KL distance. So we've done this. We have a paper coming out that does this like theoretically for just general like GTR, HKY stuff. Because like in comparative methods, n is your number of taxa, and in like model test, n is number of sites, and is it both or yeah? So that's what we're trying to get at. We do the same sort of thing here, work backwards. But there it turned out being pretty fuzzy. So I think here it'd be even fuzzier. But yeah, what are you going to say?
I was just going to ask if, like, secondarily, then it would be possible to say, okay, how much data do I need to go get for my system?
Yeah.
So how many individuals, how many loci?
I think that's what you want for grant proposals, right? You want some way to demonstrate, I have this cool question, and you need to give me money so that I can collect enough data to answer it.
And it's maybe fuzzier to be like, well, I'm going to collect 1,000 loci because it's more than 100. So.
Yeah. And I'm surprised more people don't do like parametric bootstrapping for that. Like, I imagine the model is this, I imagine these realistic parameters are this, I run it, and I need to have at least X to infer anything.
I mean, I can say as someone who sat on grant panels for this kind of work, with a number of times, is that most proposals don't do anything like that. But if your proposal does something like that, people notice it. Even if it's a really simplistic and you're making a ton of assumptions, it's still better than just saying, oh, I want to collect this much data because it's a big number. I was on this dig panel on this proposal. I mean, they had it down to like, I need 980 SNPs. And then I think I'm going to have a good answer. But, it was like reasonable to think that they could get those data. So good for them.
So I know this is all molecular-based analysis, but I just wondered if there's any consideration about in the future and including additional data such as morphology, or can you actually apply super trees to travel where you actually incorporate molecular data?
So since it's actual likelihood, if you have a way of getting likelihood of a given history from morphological data, from geographic data, you can just slap it in and add it on. So that would work. Yeah. I was thinking about having that rather than like ABC, where you have this epsilon thing, you have these summary stats. It's not really a likelihood. Here's just likelihoods. You can just add them together. So, yeah. So other thoughts on this? One thing I worry about a little bit is that users will see, oh, like 91. That means I'm really confident in that. And that's actually not what that means. Right? It means like that particular data set supports that model a lot. There could be like this one wacky gene tree that's doing it all. Yeah, so it's...
How would you know that? Like, how would you go in?
Yeah, I mean, so you could think about doing like a bootstrapping thing or something. We haven't talked about that at all, actually. You could bootstrap across gene trees. Or, yeah, I mean, you don't even have to jackknife, you just do regular bootstrapping.
Between this figure and the triangle figure, which are basically trying to show the same things with the same results, which one do you prefer?
The triangle.
Yeah, I think I like the triangle too.
I like this one.
I like this one.
I like this one.
Could you include the conclusion of the paper, the original, what model they choose using the traditional methods and what?
Well, that's true.
Well, we've looked into that. I mean,
That'd be great. We could do on this one, we could do a circle with 100% size showing the model they used. Or if they used two models.
In most cases, they consider one or two models.
So we could just circle those. That'd be great.
I mean, I like this one because it shows how data sets can really differ. The dot on the triangle plot from my data and from the House and Simmons data might have been similar, and you would think that those were interchangeable results, and clearly they're not. One is the result that I would believe in, and one is the result that I would not put much faith in.
So we have a vote. So 1 for triangle, 2 for this one. 1 or 2.
Brian swayed me.
Yeah, so 2 wins, but one gets to be.
I mean, they both have their attributes. I love the simplicity of the triangle plot.
Supplemental.
Yeah.
I mean, the triangle plot would make Jody Hay happy because it would seem to imply that the IMA was the best program to use in all cases.
Yes. Yes.
Yeah.
So if Jody's handling our paper.
Just
So other thoughts, like, so if you were reviewing a paper about phrapl, other stuff you'd want to see. Don't say GUI, please.
One more suggestion.
Yeah.
I think if you could find a data set that will best fit the isolation only, it's kind of why none of the studies will find just the species tree instead of, I don't know, is maybe the software biasing towards isolation with migration, because you don't have even a single example with just in that side of the graph.
I'm sure if we broadened our criterion to be like papers that use RaxML or something like that.
Well, these
then
were
you
all
get those,
phylogeography
but-
studies,
but
right?
Phylogeography, yeah.
And so some of them, like the Sattler data, so Jordan Sattler is my PhD student, that's what was a species delimitation study. And the groups that we used for phrapl were the 3 that were delimited in that paper. And even though the dot isn't in the tree only, it's mostly tree because it's really close to that side. So, that's, I think the Riley paper was similar to that.
I see.
And so. Actually, one thing I thought of doing was on some, we could show, above on the plot, show what the model actually is for this one and this one. So you can see, oh, wow, it's a tree with one migration parameter versus having, island, but one coalescence or something. So people can get a sense of what they are. Yeah.
How well can you actually quantify the amount of tree nests or island nests among these models? You can truly rank them 1 to 78?
There's arbitrary, there's
the number of collapses.
The number of collapses. That's why we had that. Yeah. So if everything collapses down to one thing, it's tree-like. But then you have how much migration you have. Whereas if you have 2 things collapsing, but then both, that's one step further to the right.
So
then
most of these will have 2 collapses.
Okay.
Most of these will have 1 collapse.
Yeah.
And then within increasing numbers of
migration
events.
Non-zero. That's why we have that non-zero migration rate
Okay.
thing. So you can say, okay, other one, yeah.
But this is another thing that's hard to do, right? Is to quantify similarity of models when they're multidimensional. They have these different combinations of parameters.
Yeah.
And these are all things we never thought about when we were writing the graph. We should really figure this out.
All right. Other thoughts on this? Yeah, thank you for the ideas. It's been great.
Yeah. I just think that it might be useful to make really clear the cases in which phrapl doesn't seem to perform well.
Yeah.
And that, with the simulations, I think that's gonna make it clear.
Yeah.
That's nice.
When I write methods papers, I try to. I'm not selling a method. Feel like no one on the planet knows better than I do, and it's what we do, how it fails, and so it's our sort of duty to tell people how that.
Well,
how that happens,
it's just that if you find
yeah.
a model, if you consistently find a model that phrapl is actually kind of has this tendency to choose, if you're aware of that, then that's all. It makes things way easier.
Yeah.
I don't think we've noticed that there's some model that gets chosen all the time. In these cases, we don't know what the true model is, right? So it's a little hard to evaluate.
Yeah.
But I think the important thing to notice is that when you have data that don't have very high model support for any given model, and they look more like my data down there, that's an indication that the information you have in your data probably isn't something that phrapl can use well. If yours is more like the ones on the top couple of rows, then that's a sign that, the information in your data is something that phrapl can interpret. The other thing that's hard about this is that we have this idea of performance of methods, and we've seen the kinds of plots that, like Jody Hay has used for IM, where you can show the accuracy of parameter estimates, and the precision on that and so on and so forth. That's just for one model that those kinds of figures are being developed for, so it's really easy to sort of assess how well it works. And what we're doing here is really different because we have, even in a really simplified case, dozens of models that we're relying on our ability to get some kind of a parameter estimate to calculate a likelihood value so that we can actually do the model comparison. And so what we're trying to do is hard, I think, compared to just accurately estimating a parameter. And so it's unclear to me, we want to be fair when we present this, but the fact that if we have any indication that it works at all, I think is remarkable in some ways. And so balancing between those two. Because it would be easy to look at some of these plots and think it's not working at all. But I think the goal of the program is really more ambitious, in retrospect than I expected, 3 years ago when we first talked about this. Would we have done it at all?
I would have.
So I'm just curious how you would anticipate discriminating between the cases where it may actually truly be failing to give you the right model versus either your model just wasn't parameterized with the relevant features that describe the history of divergence there, or your data themselves are not informative enough for that.
Well, we haven't looked at this, I don't think, but one way you can do it is using the grid search. I think if your grid search has likelihood values that are relatively flat for models, then that's probably an indication that your data don't have a lot of information in them. But if you have models where there's a peak in the likelihood, of a grid search, then that's probably indicative of good parameter estimates, which might lead you to think that you can use the data information you have in your data, right? I mean, is that reasonable?
Good way to think
And that's information you can extract. It might take a little bit of extra coding or defining any function, but presumably we could extract that information without much difficulty.
Okay. So kind of like from the topography of the grid search surface.
And particularly if one were going to do analyses that had a small number of predefined hypotheses and then you were using models based on these hypotheses, you might want to look at it in that level of detail.
Would you want, so bootstrapping, I guess, is, we've thought about that it's possible here to do bootstrapping across your gene trees, right? And so it increases the runtime 100-fold or so, right? I suppose you could do on the few, the top 10 models or something. Is that something you'd want as a built-in thing?
Or maybe something you could toggle.
Yeah.
Sure.
You want more flexibility? Sure, I'll take flexibility.
I don't know though, because I mean, an easier way of looking at this would be because these model probabilities are cumulative based on individual probabilities of the gene trees. So just if there's a large variance there, that might be indicative of the fact that there's one gene that is an outlier. And so to me, that would be computationally much easier than the bootstrap, and it would give you basically the information you want anyway.
RaxML's fast bootstrappy thing works actually sort of similar to that.
Yeah. So. In most cases, my intuition is that people are going to be interested, if you're using a mitochondrial gene and a bunch of anonymous nuclear markers, is there something weird about the mitochondrial gene? Yeah. And that would be, we haven't talked about whether people should even use mitochondrial genes yet.
Yeah, if you do, just use just one, or
well, yeah, I mean, there's only one, right?
Oh yeah, and there was that thing about the parameter, right? When you estimate a parameter, and if we're using mitochondrial and nuclear genes, which have different effective population sizes, if that
yeah.
How?
Oh, that's true.
Right. But so do your separate nuclear genes. I mean, to a lesser extent.
But a far lesser extent. Yeah. You could put in a toggle like gene 15 is mitochondrial, so change population size by a factor of 4 or 2, whatever it gets to. You could do that. My guess is that they're not going to be that common in the future anyway.
Mitochondrial genes?
Yeah. Especially since if you're getting 1,000 nuclear genes and one mitochondrial gene, having a special toggle for that, it might not be worth it.
But I think the data here, many of these data sets include a mitochondrial gene.
Yeah, so then it would matter.
Yeah.
Yeah.
So, it's easy to look at mitochondrial DNA as 20th century data, but everyone in this room, for the most part, still has it, is using it, and then relying on it, and so.
When probably it's a much smaller fraction of these overall data sets, but for any taxa with heteromorphic sex chromosomes, if you're then generating nuclear loci, you're going to be probably pulling some that you can't necessarily, like, a priori identify as having that ploidy difference.
Yeah.
But if you could, it'd be nice to have a setting to say, hey, the any of this should be different from the rest, if it would matter, which
it would.
I think it would, because
it would affect
the coalescence times and.
Yep, it definitely would affect the grid search.
Your idea of the subsampling thing for the bootstrap is brilliant. Because when we get like the match numbers back, we just store those, and then we can pull from multinomial, and boom, we have it right away. It's great.